Interference structure question. Two progressive sound waves, Y and Z, meet at a fixed point P. The variation with time of the displacement x of each wave at point P is shown in figure 4.1. Use figure 4.1 to state one quantity of waves Y and Z that is the same and different. I'm going to color code both waves. Y is the pink wave and Z is the green wave. One complete cycle of the pink wave corresponds to 3 milliseconds. One complete cycle for the green wave would be 4 minus 1, so you'll be also 3 milliseconds. Since seconds is the unit for period, we can state that both waves have the same period. So one quantity, both waves, Y and Z, have the same is the period. Now let's look what they have different. One is taller than the other one. So the amplitude of the pink one is 4 micrometer, and the amplitude of the green one is 2 micrometer. Just remember, amplitude is the vertical distance between the highest peak of a wave to the equilibrium line. So waves Y and Z have different amplitude. Question B, state and explain whether waves Y and Z are coherent. So we can answer that both waves have the same period, therefore the same frequency. C, determine the phase difference between the waves. Both waves have a complete cycle equivalent to 3 milliseconds. Now we need to determine what is the difference between both waves in also milliseconds. To determine the difference between both waves, we need to find a point on the pink wave that is doing the same thing at a point on the green wave. In other words, if I pick one point right here, this point on this wave is going up. And if I pick one point on the green wave that is doing the same thing of the pink wave, we can use this one here, is going up. So the difference in the x difference between both is 1 milliseconds minus 0, which is 1 millisecond. So the distance between both here is 1 millisecond. Another example, if I pick a point right here that on the pink wave is going down, so right here also is going down. And here is 2.5 milliseconds and this is 1.5 milliseconds. So the difference is also 1 milliseconds. So I feel comfortable to state that the difference between both waves in milliseconds is 1 millisecond. So phase difference is given in degrees. So now we are going to convert millisecond into degrees. So we know that one complete cycle is 3 milliseconds. So which means that 3 milliseconds corresponds to 360 degrees. Now the difference between both waves is 1 millisecond. So what will be the correspondent in degrees? So let's cancel these units. So now x in degrees is 360 divided by 3. So the phase difference is 120 degrees. So here in this space, exactly what I did at the bottom of the prior page, I just placed on the right location. So now let's go to question D. The two waves superpose at P. Use figure 4.1 to determine the resultant displacement at time t equals 0.75 milliseconds. The word superpose means overlap. So let's see what this means. So right here is the picture, and we need to spot 0.75 milliseconds. Okay, so if this is 1, this is 0.9, 0.8, 0.7, so 0.75 is right here in between. Now draw a vertical line that connects both waves, the pink and the green one, like this. Now find the corresponded where this line connected to the y direction. So this is right here is 4 micrometer, and this is right here, right between 0 and -2. So assume this is -1. So it's asking the resultant displacement. So it should be 4 micrometer minus 1 micrometer. So superpose means we need to add vertically, and we did at the time corresponds to 0.75 milliseconds. So the resultant displacement is 4 micrometer minus 1 micrometer, which is 3 micrometers. So here the answer is already with the units, so just write 3. Question E. The intensity of wave Y at point P is just I. Determine in terms of I the intensity of wave Z. First off, the intensity of a wave is proportional to the square of its amplitude. So to solve this question, we need to find the amplitude for Y and the amplitude for wave X. So right here, amplitude for the Y, which is the pink one, is the highest point here, which is 4 micrometer. And the amplitude for the green one, which is the wave Z, is 2 micrometers. So to find the intensity of the wave Z in terms of I, we need to establish a ratio. The order doesn't matter. So the intensity of the wave Z is, I'm sorry for this detail here, is not X, actually is Z. So I got the wrong letter here, is make the correction, is Z. So going back here, so the amplitude of the intensity of the wave Z is equal to the square of its amplitude. So I'm gonna use just the number, not the units. So in this case, 2 square. If you want to do that, you can. Micrometer, and well, everything here will be square, right? Over the intensity of the wave Y, which is 4 square, and the units is also square, because when we square the amplitude, everything here should be square. But it will not matter because we are going to cancel anyway. So now we have IZ, but there is one detail here. It says the intensity of wave Y is just I. So let's replace I sub Y with just I. Now we have here 4 over 16. So now we can calculate this. Is Aice in terms of I, because I is gonna go that way. This is 0.25 I. So that's the answer. In terms of I, the intensity of Z is 0.25 I. Last question. The speed of wave Z is 330 meters per second. Determine the wavelength of wave Z. So we are going to use the speed of a wave formula. The speed is 330 meters per second. The frequency, we don't have the frequency directly, but we have the period. So the period of both waves is 3 milliseconds. So, which means it's 3 times 10 to the minus 3 seconds. So the frequency here is the inverse of the period, which is 3 times 10 to the minus 3 times the wavelength. So the wavelength here is, so this is 3 times 10 to the minus 3 times 330. 3e negative 3 times 330 is a wavelength of 0.99. Two significant figures. Significant figures 2 for the final answer. That's good.